video for investigation 6B, which is called the lifting of air. And this particular slideshow only has 3 slides in it, so it's not a really long PowerPoint in terms of slides, but we've had a lot of information. In fact, in terms of content, we only have 2 slides. Now, we're going to do a lot here in a very little bit in terms of slides, so I want you to pay close attention because we're going back to Stüve diagrams today, and I'm going to fill in a lot of information on Stüves that we've been able to avoid up to this point. So listen carefully, and by all means, watch this video more than once if you feel you need to. Now, what we're going to be doing in this particular investigation is focusing on the vertical movement of air. One of the things that I don't think we do well enough in this particular class in terms of the content the AMS provides is that it's really important that you understand that in order to get clouds and precipitation in the atmosphere, it's not just about water. It's about actual lifting of air as well. If you have a lot of water vapor in the atmosphere, but there's no mechanism to lift that air, you will not get clouds and precipitation. On the other hand, if you have really, really strong upward motion, vertical motion in the atmosphere, but the air is extremely dry, you won't get clouds and precipitation. So in order to get clouds and precipitation in the atmosphere, A, you need to have water vapor in the atmosphere. You need to have a sufficient source of water. And then B, you need some sort of a mechanism to lift that air. So what we're going to be doing in this investigation is, number 1, we're going to look at some of the mechanisms that cause air to rise. And then number 2, we're going to talk about how it is that given a sufficient amount of vapor in the air, with that rising air, we get clouds and precipitation. So having said all that, let's begin the slideshow. So again, lifting of air. And what the AMS does in our first of 2 content slides is it just describes 4 different ways in which we can get upward motion in the atmosphere. So these are 4 mechanisms that cause air to rise and lead to clouds and precipitation. The first is convection, and this is not a really good slide in terms of contrast, so I'm going to actually underline the words here. So the first mechanism is convection. In the atmosphere, what we see is that energy that comes in from the sun, remember that about 46% of that energy is absorbed at the surface, and then this energy heats the Earth's surface, which then warms the air above it. The initial warming is done by conduction. In other words, the air is heated directly by the surface beneath it, and then as that air that warms by conduction warms, it will expand, and then it'll begin to rise via convection. And so what is depicted here on the top left-hand part of the slide is a convection current, where we have warm air rising, it cools as it gets higher in the atmosphere, then it sinks again where it warms and rises again. And you'll notice that where we have our rising air, we have a cloud. The second way that we can actually get upward motion in the atmosphere is by something called convergence. Now, we actually saw this, I believe, in investigation 1A or 1B when we talked about the hand twist model, and where we have counterclockwise and inward directed circulations around the centers of low pressure, and then when that air converges at the center of the low, it then rises. And so when we get convergence and rising air, again, that rising air will lead to cloud formation and ultimately sometimes precipitation. The third way, or the third mechanism that leads to upward motion, is frontal lifting. So what we see with fronts, which remember are boundaries between air with 2 different temperature characteristics, cold air on one side, warm air on the other, because cold air is more dense than warm air. As cold air advances along a cold front, that cold front will force air to rise and we'll get clouds and precipitation. Similarly, with a warm front, where we have retreating cold air, the warm air is forced to glide up and over that retreating cold air in the vicinity of the warm front, and again we get upward motion, and then we'll get our clouds. And then finally, we have orographic lifting. Orography refers to mountainous terrain. So where we have mountainous terrain, if the wind encounters the mountains obviously don't move, and so the air is forced to rise up and over the mountains, and as we get that rising air, you'll see clouds and precipitation in the vicinity of mountain ranges. And so these are the 4 primary mechanisms that lead to vertical lift in the atmosphere. Now, back to Stüve diagrams. Now remember that when I introduced Stüve diagrams a couple of weeks ago, all I want you to focus on were the pressures and the temperatures. So let's do a quick review before I actually begin to talk about what some of these other lines mean. So remember that with pressure, these are the horizontal blue lines. Remember, pressure always decreases with height, and so each one of these horizontal blue lines as we go up our Stüve diagram from bottom to top indicates a pressure level that has a lower value than the ones beneath it. So we start at 1,000 millibars, and we eventually work our way down to 100 millibars at the top of the Stüve diagram. Temperatures are along the x-axis, so each one of these vertical blue lines corresponds to a temperature, and these temperatures are in degrees Celsius. So we start with 80 below Celsius on the far left, and we warm our way up to 40 above Celsius on the far right. So these are temperatures that go from about 100 below zero or colder on the left to temperatures that are about 104 degrees Fahrenheit here on the right. So we have quite a range of temperatures, and each one of these vertical blue lines corresponds to a temperature on the x-axis. And so as you move from cold to warm and we go to these successive vertical lines, the air is getting warmer and warmer and warmer. Now remember that when you use a Stüve diagram, this is an XY diagram. So every point on the Stüve diagram has a temperature value, and you find the temperature value by just basically going down to the x-axis, and a pressure value, and you go over to the left-hand y-axis to get the pressure value. We're going to ignore altitudes. These altitudes basically correspond to the altitudes at which you find these pressures in the standard atmosphere. Now remember, the standard atmosphere is an idealized depiction of the atmosphere. It is not the real atmosphere. It's an idealization of the atmosphere. So we're not going to look at altitude when we look at our Stüve diagrams in the real world. Now, before I actually go on to reading Stüve diagrams, I want to actually define a couple of important concepts for you. And the first one is the concept of a parcel. When we take a look at what happens to air as it goes up and down in primarily the troposphere, we're going to consider an idealized volume of air called a parcel. Now, a parcel, you should think of a parcel as being something that's fairly small. So think of it like being the size of a soccer ball, a basketball, a volleyball, just not big. So something that you can actually hold in your hands. Now, I'm going to give the parcel a couple of very clear definitions that define its interactions with the surrounding air. The parcel, to begin with, is a lot like a balloon. It has flexible boundaries. So like a balloon, it can expand and contract. So the boundaries aren't rigid, they're flexible, just like a balloon. Secondly, the parcel does not exchange mass with the surrounding atmosphere or environment. So just like a balloon, the air that's inside the parcel is trapped inside the parcel, and we do not exchange air between the parcel and the outside atmosphere. So parcels do not exchange mass. So at this point, a parcel and a balloon are pretty much exactly the same. Flexible boundaries, no mass exchange. Now what distinguishes a parcel from a balloon is that parcels also do not allow energy to cross the boundary. So the total amount of energy that's inside of the parcel is constant. So we don't exchange any energy whatsoever with the surrounding atmosphere. The total energy inside the parcel is a constant. So I want you to keep these three basic rules of parcel interactions with the atmosphere clear in your head. This will probably pop on an exam. I think they're very, very important. Okay, now the term that we use to describe a boundary that does not allow energy to cross it is adiabatic. So parcel boundaries are adiabatic. So keep the word adiabatic in your head as well. I'm about to use adiabatic 2 more times below. So the first time I use adiabatic is with something called the dry adiabatic lapse rate. Now the great thing about parcels is that if we actually use these 3 rules to define parcel interactions with the surrounding atmosphere, we can actually define the rates. We can actually give a numerical rate at which temperature decreases in a rising parcel. The dry adiabatic lapse rate is the rate at which temperature decreases in a rising dry parcel. And for our purposes, dry is going to mean that the air inside the parcel is subsaturated, the relative humidity is less than 100%. So the dry adiabatic lapse rate is 10 degrees Celsius per kilometer. What that means is that for every kilometer that you lift a dry parcel the air inside of that parcel will cool by 10 degrees Celsius, which is about 18 degrees Fahrenheit. That's the dry adiabatic lapse rate. On the other hand, the moist adiabatic lapse rate, gamma sub m, is the rate at which temperature decreases in a parcel as it rises if the air inside of that parcel is saturated. And the moist adiabatic lapse rate is 6 degrees Celsius per kilometer. Now you'll notice that the moist adiabatic lapse rate is less than the dry adiabatic lapse rate. In better words, the rate at which temperature decreases in a rising saturated parcel is less than the rate at which temperature decreases in a rising dry parcel. The reason for this is that because inside of our rising saturated parcel, as we cool saturated air, some of that vapor is going to condense to form liquid droplets and basically a cloud. And condensation, if you go all the way back to our latent heat discussion, condensation is a warming process. And so as the vapor condenses to form liquid droplets inside of our parcel, latent heat is released, and that actually basically lowers or reduces the rate at which the rising parcel cools. Now you might ask yourself, hey, if latent heat is being released inside the parcel, doesn't that violate the adiabatic rule that I stated up above when I defined parcels? And the answer to that is no. Because the latent heat is being released inside of the rising saturated parcel, that heat is being released in the parcel. No energy is crossing the boundary. The energy is actually being released inside of the parcel itself. So basically, we have these two different rates at which rising air cools in the atmosphere. Now let's go to our Stüve diagram. So in addition to our pressure horizontal lines and our temperature vertical lines, we now have these diagonal green lines and these diagonal blue dashed lines. These green lines are dry adiabatic lapse rate lines, or what I like to call dry adiabats. So a dry adiabat basically will show you as you start at the Earth's surface at a given temperature, if you go up through the atmosphere, basically what a dry adiabat does is if you follow it along, it will basically show you what the temperature is going to be inside the parcel as we rise through the atmosphere. So these green lines are dry adiabats. These are the rates at which dry air in a rising parcel cools. The blue dashed lines are moist adiabats. So if you are actually rising up inside of a moist parcel, you would follow one of these dashed blue moist adiabats, and at any pressure level, this is what your temperature inside of the moist parcel would be. So it's very important that you understand dry adiabats are these horizontal green lines, and moist adiabats are these dashed blue curved lines. All right, now given that, the book, the investigation actually asks you, given the temperature of the air inside of a dry parcel at the surface, what the temperature would be after you lift it to a certain pressure level. And what we're going to do is we're going to begin with a dry parcel, and I have it right here with this red dot, that starts at a temperature of 17 degrees Celsius at 1,000 millibars. Now what I've done here is I've just simply shown you where these dots are located. I'm not actually going to do this for you. You're going to actually have to figure this out on your own. But what the investigation asks you to do is to assume that we have a dry parcel at 17 degrees Celsius at 1,000 millibars, and then to assume that this parcel is lifted to 500 millibars. Now, because the air inside of this parcel is dry, what you're going to do is you're going to lift this dot from 1,000 millibars to 500 millibars, and you're going to lift it along this green diagonal dry adiabat. And you're going to take this dot all the way up to 500 millibars. You're just going to follow this green dry adiabat until you're right here. I'm going to click again, and here's where the parcel will be located. And then you're going to have to figure out what the temperature of the parcel is. This dry parcel is at 500 millibars. Now remember, this is an XY diagram. So here's 500 millibars. This is the Y value. You go to the Y axis. In order to figure out the temperature, you drop down to the X axis, and that will give you your temperature at 500 millibars inside of this dry parcel. Then what the investigation is going to ask you to do is to again go back down to the surface, and instead of this parcel being dry, it's going to ask you to assume that the air inside the parcel is moist. In better words, the air inside the parcel is saturated. And then you're going to lift this parcel again from 1,000 millibars up to 500 millibars. Now what you're going to do here, because the parcel is saturated, is you're going to lift this parcel now along a dashed blue moist adiabat, and you're going to take it all the way up again to 500 millibars. And then this is what the temperature inside of the moist parcel will be. Now you'll notice that even though both parcels started at 1,000 millibars, you'll note that at 500 millibars, the temperature inside of the moist parcel is a good bit warmer than it is inside of the dry parcel. And the reason this is so is because of that latent heat that's released as you lift this saturated moist parcel. So as you lift this saturated moist parcel and you cool that saturated air, the vapor is going to condense, latent heat is going to be released, and you see that released latent heat reflected in this warmer temperature at 500 millibars in your moist parcel. Now the next thing that the investigation is going to ask you to do is to start again at the surface at 1,000 millibars with the pressure being 1,000 millibars and the parcel being dry, but now you're going to be asked to just lift it up to 800 millibars. And now I put a dark dot right here. So we started 1,000 millibars, dry parcel, but we only take it up as far as 800 millibars. And then the investigation says, okay, at 800 millibars, assume that the parcel becomes saturated. So if you lift this parcel from 800 millibars up, then from this point up, you're going to get condensation because you're going to be lifting a saturated moist parcel. So this basically says, okay, a cloud is going to begin to form 800 millibars, and we're going to then lift this moist parcel from 800 millibars along a moist adiabat all the way to 500 millibars. And there it is. And then finally, what you're going to be asked to do is to assume that this cloud basically rains itself out. So all of the vapor that is condensed to form cloud droplets is going to rain itself out from this cloud. And so you lose the cloud, but you still have all of that released latent heat. So we're not evaporating any liquid, we're just simply dropping it out of the atmosphere to the surface as rain. And then what the investigation asks you to do is to then say, okay, we're at 500 millibars, at this level with a cloud that's rained itself out. Imagine that this air then sinks back down to the surface again. So it's going to compress and it's going to warm. Now, the thing I want you to remember is that while rising air can cool at either the dry adiabatic lapse rate or the moist adiabatic lapse rate, sinking air is always going to be assumed to warm at the dry rate. As soon as this air begins to sink, even if it's saturated at the level where we begin, as soon as that air begins to sink, the temperature is going to increase because of compression, and the temperature is going to be higher than the dew point, and the air will be subsaturated. So sinking air is always going to warm at the dry adiabatic lapse rate. So we start here at 500 millibars, and we go back down to the surface, and what you're going to see at 1,000 millibars is that the temperature right here is going to be warmer than where we began. And that again reflects the latent heat that was released in our moist parcel as vapor condensed between 800 millibars and 500 millibars in this last example that the investigation asked you about. So you may want to focus a lot on this last slide of the investigation. Follow the dots. By all means, take a look at this, watch the video a second time, and follow the dots as I put them on this Stüve diagram so that you can remind yourself of what it is that I've done, so that you can not just answer the questions on the investigation, but understand how parcels work, understand the difference between the dry and the moist adiabatic lapse rates, understand the impact of latent heat release when heat is released inside of a rising moist parcel as vapor condenses. Okay, that's everything I'm going to want to say about Investigation 6B. Again, not many slides, but a lot of content packed in these two content slides. So if you have any questions whatsoever about the investigation or anything I've said here in this video, by all means, post a question to the discussion board or feel free to ask me live during my office hours in Zoom, during fall session, Wednesday evenings from 7:30 to 8:30, Sunday afternoons from 2 to 3 p.m. But that's it, that's all. I'll end the video now, post it on YouTube, and you'll see an announcement when it's ready for you to view.